Hi everybody. In this video, I'm gonna basically just do the lab. So images are over here. I downloaded them. I'm gonna drop them into SourceJ, and we'll kind of move back and forth between the instructions and recording this data. So in terms of just the general motion, I think I'm gonna just pick the easiest moon to do. So let's see what that is. So this is SourceJ. Gonna drag all those guys. Okay, so I'm gonna make a stack. Shout out to David for mentioning how to do that. Image stacks. So I think it just automatically made all of them a stack. And now you can use the slider to move between the images. Okay, so this is 1, it's 2, that's 3, and that's 4. So just based on this, it's a little confusing, but it's like this one is going to the left, this one's going to the left, and then this one's going to the right. So this one over here, this is a moon 2. That one should be easy to take data for. Relatively easy to take data for. Because these guys are moving in a sort of a circle, and we can't tell really where on the circle they are. But I know for this one, you see how it's like it clearly is slowing down, moving less and less distance. That means it's basically going into the part of the motion where it's like moving into the page. It's going far, 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 and now it's going into the page, and then it's going to swing around. So that is going to be a good measure of radius. And I would probably, use like this last snapshot to do that. And now these two in the back, it's kind of hard to know where in their motion they are exactly. They're at least like this far. And now moon 1 over here, it's important, I guess, just to kind of see how its distances from Jupiter are changing. So that's like the next thing for me to do. I'm really just gonna record this one data point. And you can record the distance. You kind of just doing it really rough. One way to do it is kind of just to measure, like this looks like the center of Jupiter. That looks like about the distance to the moon. And I have a pixel distance of 636 minus 415. I'm gonna pause the video real quick. How do I pause? Okay, so what I just showed you was how to kind of get a really rough reading off of just like one snapshot to, be a little bit more precise about it. We're going to use photometry to get the location of the moon, but I'm going to use just a rectangle to estimate a little bit more precisely that center. So a few pixels of uncertainty is going to add up to, tons of kilometers of difference. So all right, so that's about my rectangle. I'm going to kind of just, I'm not too familiar with the rectangular plot, so at this point now I'm going to kind of just estimate. So you can see, and I'm going to, I guess, use nicer values. Nah, whatever. That's about the edge. I'm at X is 371. Let's say that's the center. So, and then X now is at 461. Jupiter's center equals 461. Average those two. 461 plus 71. 2. And Y. Let's go a little bit up. 63. And 148. All right, so these are Jupiter's coordinates. I'm gonna put moon 1 down here. There. Moon 2. And I'm gonna take data for moon 2. I think I could do it with the stack, so let's see. And I want to highlight, like I could, if I use the photometry tool, I could hone in on this. It's not exactly at the center. Let's see, this is saying that the center is about 417,106. Oh, that's actually pretty close to what I estimated. So I'm happy with that. All right, and now I'm gonna just show you how to get data for the second moon, moon 2. So this is in the first image. That's its location. Second image, that's its location. Third image, that's its location. So it's being recorded over here. And now this I can put into my thing. So, and I can tell from the radius that this is where I started taking data for the moon. And this was for moon 2. I'm gonna get rid of this. And then it's XY, stars intensity. It's really the main data I need. It's XY. And I guess I record the radius too. I don't think I gave you data on which moons are bigger and which ones are small. And I'm just going to keep the other data for now. So if I wanted to, I could like calculate the pixel change per hour to kind of really get a speed. But I realize, the X has changed a lot right here. 60, 20, 23, 17, 16, 8, 5, 0. So like this point is its maximum distance away from Jupiter. Actually, I don't know what this is. I'm going to just say. Here's where I'm going to calculate it. My little Pythagorean theorem. Equals. I'm going to get x squared first. C22 minus static C3 squared plus D2 minus D3 squared. And I'm going to put that to the point. So this is the pixel distance from Jupiter's center. That's the pixel distance. That's the radius in its orbit. That's the radius. So that's kind of what I'm looking for as the first part of Kepler's third law. This is the value. And I'm getting about 220 at its furthest. So I can sort of repeat for moon 1 and 3 and 4, but I'm not going to really get that furthest value. I might need to just get sort of this is the max it was based on these snapshots. Okay, that's the next part of the lab. So 220, I'm going to pause here. Okay, so there's 2 more pieces of this lab that I really want to focus on. The identification part, that's kind of just fun. That is the part that should be at the end. So I shouldn't have really put this here. I would have preferred to put it at the end, after you've calculated stuff. Based on the radii, it looks like you can order like which ones are the biggest ones, which ones are the smaller ones, but it's kind of hard to distinguish. So, just putting brief reasoning over here. Which ones are the biggest and which ones are the smallest? K3L, you can do that on your own. And now the data. So I got the pixel distances. You could do that for all the moons, for the other moons. Now it's like, how do you convert? Whoops. going to just paste this over here. I don't want to do everything for you. I want you to be able to like think through some of this stuff. So I'm going to just leave it as, hey, we have a pixel distance from Jupiter's center, and Kepler's third law is in meters. So, you have to use this to convert from pixels to meters. I leave that as an exercise to the viewer. Last but not least, Kepler's third law, which I unfortunately did not put here for you, but it is in the instructions. Blah, 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 here. So for pi squared, that's all good. G, that's a constant. D is that radial distance. So after you've converted from pixels to meters, you'll have that. And now it's just the time, the period in seconds. Why seconds? Because this universal constant G is in terms of meters and seconds. So we need the time it takes for one full orbit in seconds. Unfortunately, you don't have enough data, so you need to sort of extrapolate. That's the fancy word. But using this stack, you can kind of estimate a bit. So let's see. Imagine you have Jupiter, and then you have your planet orbiting, right? If this is a basically circular orbit, then you can estimate, like, if you know the time it takes to go, from here to here, then how much time would it take to go all the way around, right? So from, let's say maybe here, if one of the moons is going like from here to there, and then let's say that was its turning point, from here to there, assuming that that's the turning point, if you know this amount of time, let's say it took 4 seconds, then how long is it going to take to complete? That's something that you can kind of think through and then estimate. Now, you weren't, like, these snapshots aren't taken at the, like, there's a bit of assumptions that need to be made. But again, like honing in on moon 2 over here, that's the one that we took the R data for. I can go to image show info, and maybe I can't. When they were individual images, you can go click show info, and what you would see is that each photo was an hour apart. So this first photo, the next photo is 1 hour later, 1 hour later. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9 hours. So it's 9 hours. So zooming in on, let's say, moon 2 over here. About how long do you think it would take to go from here to there? How long would it take to get from here to there? About. And notice, like, is it speeding up or slowing down over here? So in this portion from here to there, it was moving pretty fast. So estimate that amount on time, and then over here you have it at its turning point. So that's how you can estimate your time value. One more time, it's 1 hour between photos. So this is 1 hour, 2, 3, 4, 5, 6, 7, 8. 8 hours between those photos. Did I count that right? Let me just do it one more time. Let me double check. Yeah, so that's 8 hours. Like the time between the intervals is 8. So if you wanted to do the same for moon 1, that was 8 hours. So, you can extrapolate. How long do you think it would take to get all the way over there? Again, keeping in mind, the further it is from Jupiter, the slower it is. It starts to speed up as it goes. And now this one over here. Notice how quickly it emerges from the other side of Jupiter. So they kind of go behind like an hour apart, 2 hours apart. And it's already on the other side, like an hour after, 2 hours, 3 hours after this moon back here went. So that moon back there, that is moon 3. Moon 4 is moving quick. You can kind of estimate what portion of the orbit it is. Like assuming that's the farthest point, 8 hours later, it's about, halfway through, I guess. So, and then you can use the table to estimate again. So basically, to recap, 8 hours for moon 2 to go from here to there. And then I think based on what I shared with you, you can kind of rerun the video to estimate maybe the periods of these guys and this guy. Okay. And then last but not least, so kind of collecting all that data, putting it down. If you have Salsa up and running, you can get even better data by taking the photometry results for each of the moons as they went. And then basically you can combine those in a graph. So this is something I do with my physics class a little bit, but with you guys, I'm not sure if you know how to do it. So let me just draw this. Basically, the equation is m is equal to 4 pi d cubed. That's a pi, by the way. Big G over t squared. So I need this in a form of y equals mx plus b, where I want the slope to literally be my mass value. In this case, it just happened to be m. So something I can do, there's multiple graphs you can make. But the simplest, if I'm gathering t squared data and d cubed data, is to graph, let's see. I'm going to just, basically I want this m term to match up with this m term, and then to have either t squared or d cubed in the x. And so what does that look like algebraically? Really just solving for, or moving the t squared over. So I'm going to get 4 pi, oh, and there's a squared value there. Don't forget that. 4 pi squared d cubed over g is equal to mt squared. And then I'm actually going to isolate the d cubed. So d cubed equals m t squared g. How should I write this? I'm going to move this over, so it's going to be g over 4 pi squared times m t squared. And let me just illustrate this on a graph. So I wish I could just scroll down. I ran out of space here. All right, so this is the algebra. If you need to see it again, just rewind. But this is what I've solved for. And now I basically want to say I have this in the form of y equals mx plus b. If I say that, hey, this is my y, this whole thing is my m, and then this is my x, t squared. So on a graph, if I was to graph d cubed on the y-axis against t squared, I would expect a straight line, the slope being g 4 pi squared times the mass of Jupiter. And so once I get this number, let's say it's 2, I divide 2, or I said 2 equal to g m over 4 pi squared, because it's equal to the slope, and solve for m. I don't know if that's the quickest, simplest way to do it, but that's a way to do it I can think of off the top of my head, and I can show you. So that's how you would then estimate the mass of Jupiter. Oh, I could scroll down. That's how you can estimate the mass of Jupiter finally, and then you can reflect and give feedback. That's about it. This you can do it on your own. Make sure you just convert. Units have to be in seconds and meters. Yeah. Okay. Hopefully that's enough for you to be able to take it. Hope that was fun. Take care, guys. Maybe not fun, but like hopefully it's kind of cool that you did it. Take care. Bye.